Okay, now continuing with ASHRAE Standard 514. Most of us are familiar with ASHRAE 188, the document on the left on your screen. It was first published in 2015 and became the foundation for healthcare water management programs across the country. The primary focus of ASHRAE 188 was Legionella prevention, and it did a tremendous job helping healthcare facilities develop structured water management programs. However, over time, we learned something important. Legionella is not the only organism creating risk in healthcare water systems. Facilities began seeing increasing concerns related to organisms like Pseudomonas, NTM, Klebsiella, and other opportunistic waterborne pathogens. That's where ASHRAE 514 comes in. Rather than replacing 188, ASHRAE 514 expands upon it. They complement each other. It takes the same risk management principles many of us already know today and broadens the focus to include microbial, physical, and chemical hazards throughout the building water system. The easiest way to remember the difference is this. 188 asks, how do we manage Legionella risk? 514 asks, how do we manage all significant water-related risks? Another important point is that ASHRAE 514 aligns very closely with what CMS and Joint Commission surveyors are increasingly looking for today. Risk assessments, documentation, verification of control measures, ongoing monitoring. In many ways, ASHRAE 514 reflects where healthcare water management is headed. If ASHRAE 188 gave us the foundation, ASHRAE 514 builds the next level of that house. It takes us beyond a single organism and moves us towards a comprehensive water risk management program. Let's look at how 514 accomplishes that through its 7-step risk management methodology. One of the reasons 188 became so successful is that it gave healthcare facilities a structured process for managing risk. 514 uses that same framework. Notice that nowhere on the slide does it say, buy this technology, install this product, test for this specific organism. That's because ASHRAE 514 is not prescriptive. Instead, it provides a roadmap for identifying, assessing, and controlling risk. Your first step is assembling the water management team. In my experience, this is where organizations either succeed or they struggle. Water safety is no longer owned solely by facilities. We need everyone involved, every department. If only one department owns the program, blind spots are inevitable. Once the team is assembled, we move into understanding the system. You want to describe your building water system, identify hazards, assess the risks. This is where you should be asking questions like, where does water stagnate? Where are our vulnerable patients? What devices do we have that use water? What happens during construction? What happens during a boil water alert or a boil water advisory? After those risks are identified, the next step is implementing controls. These controls may include temperature management, flushing programs, testing, disinfection, filtration, or a combination of these approaches. Implementing controls is only half the battle. The standard then requires monitoring those controls and verify that they're actually working. And finally, document everything. If it's not documented from a survey perspective, that means it didn't happen. The key takeaway from this slide is that 514 isn't asking hospitals to create an entirely new process. It's asking to apply a structured risk management approach to all significant water hazards, not just Legionella. So now that we've discussed the framework, let's talk about the actual hazards 514 wants us to evaluate. And the standard groups those hazards into, the standards groups those hazards into 3 categories, that being microbial, physical, and chemical. One of the biggest differences between 188 and 514 is that 514 broadens the conversation significantly. Rather than talking just about Legionella, the standard asks us to evaluate three categories of hazards that may exist within our building water management system. What I like about 514 is that it recognizes water safety is not just about bacteria. Sometimes the problem is biological, sometimes it's plumbing design, sometimes it's water chemistry, sometimes it's all a combo of those three. Let's take a closer look at each of these hazard categories, starting with what most healthcare facilities are already familiar with, microbial hazards. The first category we'll discuss is microbial hazards. When most people hear waterborne pathogens, they immediately think of Legionella. Legionella is important because of the severity of disease it can cause and the attention it receives from regulatory and accrediting organizations. However, Legionella is only one of the many organisms found in healthcare water systems. As I mentioned earlier, other pathogens like Pseudomonas, NTM, Klebsiella, and many others are all organisms naturally present in water and can colonize plumbing systems, fixtures, ice machines, water treatment equipment, and water-associated devices. What makes healthcare unique is the patient population. Healthy individuals may never become ill from exposure, but immunocompromised patients, transplant patients, oncology patients, NICU patients, and other vulnerable populations can be at significantly greater risk. These organisms don't appear overnight. They thrive in conditions that allow them to survive and multiply. Again, stagnation, temperature control, maybe low disinfectant residuals, scale, sediment, and importantly, especially biofilm. That's why modern water management programs focus not only on detecting organisms, but on controlling the environmental conditions that support their growth. As we move through this presentation, you're going to notice a common theme. Successful water management isn't about chasing one pathogen. It's about understanding the conditions that allow pathogens to persist and implementing multiple barriers to reduce risk. The second category is physical hazards. While microbial hazards are the organisms themselves, physical hazards are the conditions within the building water system that create opportunities for those organisms to grow and spread. These are often the root causes that water management teams can directly influence. Examples include dead legs, low flow areas, stagnation, oversized plumbing, inadequate circulation, poor temperature control, and aging infrastructure. For example, if water sits stagnant in a section of pipe for extended periods, disinfectant residuals diminish, temperatures drift into growth ranges, and biofilm begins to develop. Once that occurs, the environment becomes much more favorable for pathogens. Temperature management is a critical consideration. Water that's too cold or too hot creates challenges. Many healthcare facilities must balance pathogen control with patient safety. We want hot water temperatures that discourage microbial growth, but also protect patients from scalding. One of the key concepts in 514 is that facilities should focus not only on testing for pathogens, but also on identifying and correcting the physical conditions that contribute to risk. In many cases, it's easier and more effective to control the environment than it is to react after a positive culture or water-related event occurs. As you review your own facility, ask yourself, where are my areas of stagnation? Where are my low-use fixtures? Where might water be sitting longer than intended? Those locations often become your highest risk areas within your building water management system. The third category is chemical hazards. These are the risks associated with the chemistry of the water itself. While they may not receive as much attention as Legionella or other pathogens, they can have a significant impact on patient safety, equipment performance, and regulatory compliance. Examples include disinfectant residual, corrosion byproducts, hardness, chlorides, conductivity, pH, dissolved solids, and chemicals introduced through water treatment processes. For those involved in sterile processing, this is where AAMI ST108 becomes important. ST108 establishes specific water quality requirements for many of these parameters because water chemistry directly affects cleaning effectiveness, equipment longevity, and ultimately patient safety. Poor water chemistry can contribute to scale buildup, corrosion, spotting, instrument damage, shortened equipment life, and inconsistent reprocessing outcomes. Chemical hazards can also influence microbial risk. For example, inadequate disinfectant residuals may reduce the ability to control bacterial growth, while corrosion and scale can create surfaces that support biofilm formation. One of the key messages from both ST108 and ASHRAE 514 is that water quality is not just a facilities issue. It's not just an infection prevention issue. It requires complete collaboration between all departments. The goal is to understand the chemistry of the water, monitor it appropriately, and ensure it remains within acceptable ranges for both patient safety and operational performance. One of the questions I get all the time is, should we focus on point of entry treatment or point of use treatment? The answer is usually both. 514 is built around risk reduction. Most successful programs use multiple layers of protection rather than relying on a single control measure. Point of entry solutions include things like secondary disinfection systems, water chemistry management, softening systems, RO systems. These systems treat large volumes of water before it moves throughout the building. The advantages are obvious. One installation can affect the entire facility. They're effective at reducing overall microbial burden and managing water chemistry. But there's also a limitation. Water can enter the building in excellent condition. It then travels hundreds or thousands of feet through piping. It encounters dead legs, low use outlets, temperature fluctuations, biofilm, stagnation. That's where risk can reappear. Point of use solutions provide what many people call the last mile of protection. Instead of treating water at the building entrance, we're protecting water immediately before patient use. This is important in high-risk environments like burn units, oncology, transplant, NICU, or any other areas where immunocompromised patient populations exist. That's really what ASHRAE 514 is encouraging us to think about. Not whether one approach is better than the other, but whether our control measures are appropriate for the risk we're trying to reduce. The most successful water management programs rarely depend on a single strategy. Instead, they combine multiple controls to create layers of protection throughout the water's journey from entry into the building all the way until it reaches the patient. One of the questions I hear occasionally is, does ASHRAE 514 really apply to me? When you look at the criteria outlined in the standard, the answer for most healthcare organizations is probably yes. If your facility treats immunocompromised or high-risk patients, you're within the scope. Honestly, most hospitals have at least some patient population. Next, think about how water is used in your facility. Water is not just for drinking. It's used in medical device reprocessing, wound care, humidification systems, respiratory therapy. Anywhere water comes into contact with a patient, the risk profile changes. The standard also recognizes that healthcare water systems are complex. You have long pipe runs, storage tanks, mixing valves, multiple wings and departments, multiple buildings on a campus, renovations and expansions over decades. Complexity creates opportunity for stagnation and biofilm development. It's one of my favorite sections because it directly addresses many of the blind spots we talked about earlier. Showers, ice machines, humidifiers, decorative water features, cooling towers, and eye wash stations. Notice that several of these are not traditionally considered part of infection prevention programs. If patients are spending the night in your facility, your responsibility changes. Water quality becomes more than a facilities issue, it becomes a patient safety issue. And finally, if your facility is surveyed by CMS, Joint Commission, DNV, state health departments, the water management expectations continue to evolve. Surveyors are asking not whether you have a program, but whether you can demonstrate that the program is effective. Now let's talk about something that gets a lot of attention whenever people read ASHRAE 514 for the first time. The standard doesn't just identify hazards, it also discusses potential control measures. One of those control measures is filtration. ASHRAE 514 specifically states that FDA Class 2 filters may be used to provide a barrier to the transmission of microbial hazards and potable water in areas used to house or treat inpatients. I think that's important because this is not a manufacturer's recommendation. This is published consensus guidance from the ASHRAE committee. Now notice what the standard does not say. It does not say every outlet should be filtered. It does not mandate a specific product. It does not require filtration throughout the entire building. Instead, it recommends evaluating risk and applying controls where they make sense. The third category is often overlooked: non-medical equipment that uses water or is cleaned with water. That includes ice machines, eye wash stations, bottle fillers, drinking fountains, equipment that may not traditionally be viewed as part of an infection prevention strategy. 514 recognizes that risk isn't determined by whether something is classified as a medical device. It's determined by how water reaches the patient. So why specifically FDA Class 2? What makes those different from other filtration technologies? Earlier, we saw 514 specifically reference FDA Class 2 filters as a microbial control strategy in certain healthcare applications. So naturally, the next question becomes, what exactly is an FDA Class 2 filter? Easiest way to explain it is that these filters are regulated as medical devices that have received FDA 510(k) clearance for their intended use. They've been validated, there's regulatory controls, there's verified claims, there's accountability, practical applications. The standard recognizes these filters may be used in applications where water quality has a direct impact on patient safety. And the key takeaway is that not every filter is FDA Class 2. The key takeaway is that 514 specifically references validated microbial barriers when facilities determine that filtration is an appropriate control measure. In other words, the standard is not just asking whether a filter exists. It's asking whether the filter's performance has been validated for that application. This takes me to my favorite category, ice machines. When people think about waterborne pathogens, they don't think about, or I should say, they think about showers, faucets, cooling towers. But many times ice machines don't receive that same level of attention. These are actual photos taken from healthcare facilities. None of these machines were intentionally neglected. They're simply operating in environments where biofilm, scale, and contamination were allowed to accumulate over time. Ice machines present a unique challenge because they combine several risk factors. First, they contain water. Second, they contain moisture. Third, they have surfaces that are difficult to inspect and clean. Fourth, they produce a product that is directly consumed by patients. That's a very different risk profile than many other pieces of equipment. One of the biggest misconceptions I hear is it's an ice machine, so bacteria can't grow there. That's not true. The ice itself is cold, but the internal components of the machine often operate as the perfect breeding ground for bacteria. Those temperatures in an ice machine often operate much higher than people realize. In some locations inside the machine, temps can reach 100 degrees, which is within the growth range for organisms like Legionella, Pseudomonas, and NTM. If you look closely at these photos, what you're not seeing is simply dirt. You're seeing scale, biofilm, moisture retention, areas that can support microbial growth. Remember, once biofilm establishes itself, disinfection becomes significantly more difficult. The point isn't that every ice machine is contaminated. The point is that every ice machine has the potential to become contaminated. So you want to make sure it's included in a structured maintenance, cleaning, and monitoring program. Now that we've talked about why ice machines can become a blind spot, let's look at what happens when maintenance and sanitation aren't performed consistently. Most regulatory findings involving ice machines don't start with Legionella. They usually start with something much simpler. That being discolored ice, scale deposits, slime buildup, odors, contamination, elevated bacterial counts. These are often early warning signs that conditions exist which may support more significant microbial growth. When I visit facilities, I like to ask a few simple questions. How often do you descale your ice machines? How often are your evaporator plates cleaned? How often are drain pipes inspected? Your supply lines sanitized? And perhaps the single most important question, what type of water are you using during the cleaning process? This is a really important point. If we're using untreated utility water to rinse or clean equipment after sanitization, there's a possibility you're reintroducing organisms right back into that machine. In other words, you may be cleaning the machine and contaminating it again at the same time. Are ice machines really that important? Yes. Not because I'm saying it, but because the ASHRAE 514 committee says it. They're referenced 28 times throughout the document. Think about that for a moment. Out of every water-using fixture and piece of equipment in a hospital, ice machines are discussed 28 different times. In fact, ice machines are important enough that 514 gives them their own dedicated section. Why? Because they use potable water. It produces an ingestible product. It stores water internally. They're difficult to clean, and they're frequently used by patients, staff, and visitors. The other thing I want to point out is that when ASHRAE 514 discusses microbial barriers, ice machines are specifically included within those recommendations. The standard recommends evaluating FDA Class II filters as a microbial control measure for high-risk patient areas, medical devices utilizing water, and non-medical equipment that uses or is washed with water, including ice machines. If ASHRAE 514 is given this much attention to ice machines, we should probably be asking a simple question. Are we really filtering and protecting these systems the way we think we are? This is an important slide. Let's talk about another blind spot I see frequently when discussing water safety programs. Many facilities tell me we're already filtering. My next question is always filtering for what? Many free filters are designed to remove sediment, rust, dirt, and particulate. They do a good job of protecting equipment from physical debris. However, removing sediment and providing a microbial barrier are two completely different objectives. Sediment filters are not designed or validated to retain bacteria. One thing I always encourage facilities to look for is clear filter housings. You don't want them exposed to ambient light, as they can create an environment where biological growth may occur inside the housing. It's important to understand carbon filtration. It's a chemistry solution. It's not a biological barrier. In fact, carbon media can cause a nutrient-rich environment if maintenance intervals aren't followed appropriately. That's why understanding replacement schedules and system design is so important. You want to make sure you're not being offered a false sense of protection. If I walked into your facility today and asked which filters are installed on your ice machines, would you know exactly what those filters are designed to do? Is it scale reduction, chlorine reduction, sediment removal? The takeaway isn't that carbon filters are bad. The key takeaway is we need to understand what problems we're trying to solve and whether the filtration technology we're using is actually designed for that purpose. And that brings us to perhaps the most important thing every facility should understand about commercial filtration systems: the warning label that's printed right on the filter. I like to call this the fine print slide. How many of you have actually read the warning label on the filters installed in your facility? I would guess most haven't. When the label says, do not use with water that is microbiologically unsafe or water of unknown quality without adequate disinfection. In other words, the manufacturer is telling us exactly what the filter was designed to do and what it was not designed to do. A filter can be very effective at reducing sediment or reducing chlorine, improving taste and odor, but it may not be intended to provide a microbial barrier. Let's talk about something that most of us probably never think about during equipment maintenance. What water are we actually using to clean the equipment? Warm water, fresh water, clean water, hot water. But very rarely do the instructions define the microbiological quality of that water. So here's the question I ask. If you're spending an hour cleaning and sanitizing an ice machine, what happens if the final rinse water contains bacteria or biofilm organisms? There's a possibility you're reintroducing contaminants immediately before putting that machine back into service. Speaking of overlooked processes, let's talk about another area that rarely gets included in maintenance discussion: supply lines and connections that feed these systems. These photos came from actual healthcare environments. The challenge is that these supply lines remain wet 24 hours a day, 365 days a year, providing a perfect environment for scale accumulation, biofilm formation, and microbial growth. What we're looking at here is not a rare occurrence. Want to make sure these supply lines are being changed ever so often. It's one of the things nobody thinks about until there's a problem. That's really the theme of ASHRAE 514. Look beyond the obvious and identify hidden risks throughout the entire water journey. We talked about biofilm, supply lines, ice machines, hidden contamination points. One of the questions that normally follows is, how do we address the portions of the system downstream of the filter? One of the biggest blind spots in many maintenance procedures is the section of tubing or hose located downstream of the treatment device. These areas remain wet, are rarely inspected, and in many cases are not addressed within manufacturer cleaning instructions. Yet they're still part of the water pathway. Think about what happens during a filter replacement. We remove the old filter. We install the new filter. What about the tubings, fittings, dispensers, and components that were connected to an old filter? You want to make sure that you have eyes on this and that those are being changed as well. That's really the theme here with 514. We're going to look beyond the obvious fixtures and identify hidden risks throughout that entire water pathway. You want to be careful around temperature. Notice this chart. and the perfect growth temperatures for Legionella. You want to notice how long it takes at what temperatures in order to kill Legionella if that's in your facility. Very helpful slide. So all those factors, we covered a lot of ground. Ice machines, supply lines, water temperature, commercial filtration, maintenance practices. So before we move on, I'm going to leave you with a few questions, what you should be asking. First, do you have clear or translucent filter housings exposed to ambient light? Second, when a filter is installed, can it be primed without exposing the downstream equipment? Many facilities teams will prime a filter by running that water through the ice machine, which is definitely something you want to stay away from. Remember the warning labels we spoke about. Remember, we should be looking at biological filters that are FDA cleared class 2. Before we move on, we're going to summarize. First, bacteria and other waterborne pathogens can grow within ice machines if maintenance, cleaning, water quality, or temperature controls are inadequate. Second, CMS has identified ice machines as critical control points. It's because they're producing a product that's consumed by patients, visitors, and staff. In other words, this is not a facilities concern, it's a patient safety concern. Third, ASHRAE 514 recognizes validated microbial barriers can be used as one of several risk reduction strategies if facilities determine they're appropriate. If your facility's water management program currently overlooks ice machines, ASHRAE 514 is essentially telling us it's time to reconsider that approach. Up to this point, we talked about standards, risks, maintenance practices, and control measures. I thought it would be helpful to look at a real-world example of what happens when a facility evaluates one of these risks and implements additional controls. In this case, the focus was hospital ice machines. As we've discussed, ice machines can develop biofilm, accumulate contamination, and become a potential growth source of bacteria. This facility recognized two important limitations. First, chemical disinfection alone does not remove biofilm. It may reduce organisms, but the biofilm can remain attached to surfaces. Second, many commercial filters are designed primarily for scale, sediment, chlorine, taste and odor, but not necessarily microbial retention. This facility elected to install FDA Class 2 ultra filters downstream of their existing commercial filtration and evaluate that performance over a 6-month period. What's important here is that the ultra filters weren't replacing the commercial filters, they're complementing them. One of the most interesting findings was what physically retained by the ultra filters during operation. The filtered water remained clear, while the material captured and removed from the incoming water became very visible during the evaluation. Another concern people have is, will filtration dramatically reduce flow? In this evaluation, despite the amount of material captured, the filters maintained acceptable flow rates throughout the study period. What I like about this example is that it reflects exactly what 514 is encouraging facilities to do. Identify risk, evaluate control measures, verify performance, and document your results. You want to be looking to see, are eyewash stations on your risk assessment today? This is another challenge. These aren't always tested. Someone might have an issue, they go to the eyewash station, use it, and the first thing they're seeing is stagnant water or temperature affected water coming out of that outlet, which is not good. Let's not forget drinking water fountains or bottle fillers, hydration stations. Many people view them as simple drinking fountains, but from a water management perspective, it's much more complex. One thing I always look for is dead space or low flow areas within the fixture. The point is that bottle fillers are not dangerous. The point is ASHRAE 514 encourages us to evaluate every water using fixture through a risk management lens rather than assuming it's safer or safe because it's familiar. In summary, we talked about 514, expanding on healthcare water management beyond Legionella. It requires facilities to evaluate three categories. One of the biggest differences between 188 and 514 is 514 is built around risk assessment. Third, the standard recognizes FDA Class II med devices as a validated microbial control strategy in appropriate applications and patient care environments. In healthcare, validation matters. Be aware of your ice machines, eye wash stations, drinking fountains, bottle fillers, medical devices, sinks, and showers. There's rarely a single solution that will address every risk. If I had to summarize 514 in one sentence, it would be this: understand your risks, validate your controls, and verify that they're working. Up to this point, we focused on water as it moves throughout the healthcare facility and eventually reaches patients, visitors, and staff. Now let's shift our attention to another area where water quality is absolutely critical: medical device reprocessing. Because while ASHRAE 514 focuses on protecting people from water, AMI ST108 focuses on protecting patients through the water used to clean, disinfect, and sterilize medical devices. I'll pause here and continue with the next chapter.